Okay, welcome back. And now we're going to do some graphing. So we're going to do, I think, 4 examples of graphing functions. Okay, and so I'm going to go through those steps to graphing each one of these. So just pay attention, and then again, just practice the stuff. Okay. When it comes to graphing, definitely assume that there's going to be at least one on an exam that you're going to have to show your work for. Okay, and so this is how you would show your work. Go through these steps. Okay. So the first thing is the domain, right? So the domain of the function here is all real numbers. It's a polynomial. You can expand this out and you get a polynomial. So the domain is all real numbers. Okay. And what else? Then step 2, we want to find the x and y intercepts, right? Well, the x-intercept is y is 0, right? The y-intercept is where x is 0. So the y-intercept is the easier of the two. So the y-intercept is the point where it crosses the y-axis, right? So that happens when x is 0. So if x is 0, you get negative 1 squared, which is positive 1. And here you get 2, so it's going to be 0, comma 2. And the x-intercept, is where y is equal to 0. So we set the function equal to 0, and we solve for x. Okay, so when is this x? Now here, because it's factored, it's easier because all you have to do is use the zero product principle and say, okay, one of these factors, at least one of the factors has to be 0. So that would mean x would be 1, right? So one of the x-intercepts is 1, comma 0. And the other x-intercept is negative 2. So negative 2, comma 0. Okay, so now we've got our y-intercept and 2 x-intercepts. Okay, so the next thing they want us to do is evaluate end behavior. Okay, so now this is where we're going to take the limit as x goes to positive infinity, right? And the limit as x goes to negative infinity. Okay? So what happens here? Well, a couple things you can do, right? So one, this is a third degree polynomial because again, the largest power of x, you're going to get x squared here. X times x squared will give you x cubed. So this is going to be a third degree polynomial. So we know that they're going to be opposite tails, right? And the leading coefficient is going to be positive in this case. So it's going to have a general positive slope to it. So opposite tails, general positive slope from left to right. And so it's going to look something like that. Okay, it might do something in the middle, but the general end behavior is it's going to go up to the right and down to the left. Okay, but if we take the limit, right, as x approaches positive infinity of f of x, right, well, this is going to go to positive infinity. This is getting large positive, this is getting large positive, so positive times a positive is positive, right? So this is always going to be positive here because of the square. So this is going to be, what the sign of this thing is going to be determined by the second factor. So we know as x goes to positive infinity, it's going positive, and then the limit as x approaches negative infinity of f of x is negative infinity. Okay? Okay, so anything else Okay, so that's step 3. So I've given you a couple ways to approach how to figure out end behavior for that one. Okay, so we know it does something like this. Okay, now, step 4, we want to look for vertical asymptotes. Well, since it's a polynomial function, there are no vertical asymptotes. So, vertical asymptotes, none. And now we're going to look at the first derivative, step 5. So the first derivative, and this is where I'm going to expand it out. So instead of using the product rule, so this is going to be okay, and so we get x cubed and so we get x cubed minus 3x plus 2. Okay, now the first derivative is going to be 3x squared minus 3. Okay. And so in this case there are going to be 2 critical points because we can factor this into 3 times x squared minus 1, which is the difference of 2 squares. So that's going to be 3 times x minus 1, x plus 1. Okay, so we get 2 critical values. At plus and minus 1. Okay, when x is equal to plus or minus 1. And so we're going to divide the interval into 3 intervals. 3 subintervals, I should say. Right? So you've got from negative infinity to negative 1, and then you've got from negative 1 to 1, and then you've got from 1 to positive infinity. Okay? And so then we're going to test each one of those, right? So in this case, we might want to use negative 2. Okay? And when x is negative 2, we get a positive number, right? X is negative 2, we get a positive number, so this is going to be positive here. 0 gives us what? 0 gives us a negative, so we're going to be negative in there. And then positive 2 will give us positive, so we positive. So what does this tell you? It tells us that it's increasing in the first interval, right? Decreasing in the second interval, and increasing in the third interval. Right? Okay, so then, step 6 is we take the second derivative. Oh, and by the way, it changes sign, so we know we have a, what? It goes from positive to negative, so we have a local maximum at negative 1, and then it goes from negative to positive at positive 1, so we know we have a local minimum at at positive 1. Okay, so we can also write that down. So we got a maximum at negative 1. And so the maximum point would be what? It'd be 1, so negative 1 hold on a second here. So it'd be negative 1 comma 4 is where the maximum, local maximum is at. And then the minimum, the local minimum, is going to be located at 1. One comma 0, it looks like. Okay, now the second derivative is what? Second derivative is going to be 6x. Okay. And so now, since here we're going to find the second derivative 0 at when x equals 0, right? So x equals 0. And so we're going to split up the interval into two intervals, negative infinity to 0 and 0 to positive infinity. And then we're going to test both sides. Why are we doing this? For concavity. Okay? So here, if we put in 1, what do we get? Again, we're looking at positive, negative, right? So here we pick negative 1, stick it into this, and it's negative, which means it's concave down. So it looks like that. Or curves down like that. And then this one's positive, because if I stick in 1, I get positive numbers, so this is concave up. So it curves up. Okay, so now, is there anything else? Oh, so since it goes from concave down to concave up, that means 0 is an inflection point. Okay, so now we can graph this thing. With all the information we have, we can graph it. Okay? So let me make some room here. So I'm going to use my and so let me okay. So now, I'm going to take all the information and graph it on here, okay? So we got a y-intercept at 0, 2. we've got x-intercepts at 1, 0. Notice that there's a minimum at 1, 0, 2. So there's an intercept at 1, 0, which is right there, and negative 2, 0, which is right there. So I've labeled all those, graphed all those. Now, I know it's going to go up to the right and down to the left. There are no vertical asymptotes. And I know that it's there's a maximum point at negative 1, 4. So let's do that one. Negative 1, 4, which is down here. Let's say right about there. And then there's a maximum. Hold on. Oh, hold on. Negative 1, oh, wrong one. Wrong way. So negative 1, 4 up here. Somewhere. Yeah. Say about right there. Okay? And then a minimum at 1, 0. So it's already marked. That's the one of the x-intercepts. Okay? So I know it goes down here like that, and I know it has to go up over here. And so there's a lot of information. So I can already graph this thing based on what I have graphed. Okay? Now it says concave up to the left of 0, concave down, concave down from the left of 0, concave up to the right of 0. Okay? So that means there's an inflection point at 0, so which is right there. So this is going to look like this. So it's going to be like that. So it's going to look something like that. Okay? So there's an inflection point here, so maybe it's a little more curved, right? So anyway, we're just sketching the graph. So there it is. That's what it looks like. Have a great day.